7 here, I think. So last chapter we talked sort of about last time equations, how to balance equations. Remember that when we balance equations, it is just the coefficients that we change, which are those numbers that come in front. When it is completely balanced correctly, you should have all whole numbers for the coefficients, and they should be the simplest set of whole numbers. Remember that you can use a fraction to balance an equation, but you do need to get rid of the fraction when it's all said and done. You should classifying reactions. So we're going to start with reactions in aqueous solution, and aqueous really does mean a water environment in most cases. Is basically a solution. And again, it is those guys that get that AQ sort of symbol next to it. Remember that an aqueous solution is made by really dissolving a lot of times a solid in something else like water, which makes a solution. So again, if you took some sodium chloride that was a solid and you dissolved it in the water, you would get a sodium chloride solution. So when we talk about aqueous solutions, a solution really is a homogeneous mixture of two things. One part of a solution is known as the solute, and that is the smaller part of the solution. So the solute here is, in my sodium chloride example, would be our sodium chloride would be the solute. And the larger part of the solution is the solvent. So like in my example there, the water would be the solvent. And once again, when we take both of these things, we do make a sodium chloride solution that would get the aqueous symbol, and it would obviously be in the liquid state in that case. So the solute is always the smaller part of the solution. Solvent is the larger part of the solution. In a lot of cases, water is oftentimes the solvent that is used. It's not always the best solvent, but a lot of times it is used in a lot of cases, especially with things that are polar, things that are ionic. Water is a really good solvent for. Things that are non-polar, water is not a very good solvent for, and we'll get into some of that a little bit later on. How do you know what is the solute when you have a solution? Well, it's pretty simple. Pretty much the name of the solution is the solute. So if you have a sodium chloride solution, sodium chloride is the solute, it's the stuff dissolved in it. If you have a calcium chloride solution, then calcium chloride would be the solute. So kind of whatever the name of the solution is really the solute that is sort of dissolved in there. Now, when we talk about solutions, when we talk about what happens in aqueous sort of situations, an electrolyte is sometimes referred to. An electrolyte is a substance, again, that will basically conduct electricity. And really the reason it's able to do that is when an electrolyte is dissolved in solution, it will create ions. So the creation of these ions is what helps it conduct electricity really well. A non-electrolyte, on the other hand, is something that will perhaps still dissolve, but will not create any ions. And because it doesn't create any ions, it is not going to conduct electricity. So, for example, something like sugar is an example of that. Sugar is carbons, hydrogens, and oxygens. Although it will dissolve, for example, in water, will not create any ions. And really the lack of ions there will mean that it will not be able to conduct electricity really well. When we talk about electrolytes, there are a few different types of electrolytes. A strong electrolyte is something that will pretty much 100% break apart in solution. So in solution, you do not have any of the sort of whole units still together. They have had completely broken apart into ions. So for example, in a sodium chloride solution, if you had a solution of sodium chloride, really what you have are just the sodium ions that are floating around and the chloride ions that are floating around. There really is no more sodium chloride units still together. in a solution, and that is basically a strong electrolyte. Because it will 100% break apart a strong electrolyte, it's able to conduct electricity really well because you have just a lot of ions in that solution. So a lot of ions in that solution is going to allow really everything to sort of be complete in terms of the electrical current and all that, and it will conduct electricity really well. Sometimes people use light bulbs to sort of illustrate this, and if you had a light bulb, it would shine very bright. If you had a light bulb that was hooked up to some electrodes that you put into a strong electrolyte sort of solution. So it will conduct electricity really, really well. It'll be very bright. Most ionic compounds are strong electrolytes. So most ionic compounds that go for a swim, they pretty much will break 100% apart. Also, a lot of strong acids and strong bases are also strong electrolytes. So things like hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydriodic acid. These are some examples of some strong acids. They are also, again, strong electrolytes. Things like sodium hydroxide, potassium hydroxide. These are some strong bases. They are also basically strong electrolytes. So if you had something like hydrochloric acid solution, again, basically 100% of it will break apart into H plus and Cl minus. So if you had a solution of hydrochloric acid, you pretty much have all your H pluses floating around and your Cl minuses floating around. Again, you would not have any of the HCl units basically still together in that solution. It would also obviously conduct electricity really, really well. Any questions on that there? So a weak electrolyte, for example, though, you had a weak electrolyte, it will basically stay together, but will produce a few ions. So, for example, HF, which is a weak acid, will break apart into H plus and F minus in solution. The difference is, though, you have just a few of these ions that are being produced. You mainly have the HF unit still together. So if you looked at sort of a bad shaped beaker there of HF, you mainly have sort of these HF ion molecules together, but you still are producing a little bit of ions in there as well. So mainly stays together, but still able, because it's still able to produce a little bit of ions, it is still considered an electrolyte. It is still able to conduct electricity. But if you kind of go with the light bulb example, and you stuck a light bulb with the electrodes attached to the light bulb, it would go off, but it would be very dim. So it would still be able to conduct electricity, but it'd be kind of anywhere near the amount of electricity that a strong electrolyte could do. Because again, in a strong electrolyte, all it has to do is go for a swim and you got a ton of ions. Here, you're just going to have a few ions. The other difference is a lot of times in weak electrolytes, we will see these arrows that head in both directions, which once again means this is a reversible reaction where there is a forward direction heading from reactants to products. But at some point, the products will combine and go the other way and come back to make some of the reactants. So it's really a reaction that kind of goes directions. And that is a major difference between that and a strong electrolyte, which is pretty much a one-way street. Everybody is dumping off into the product side. Nobody from the product sides are coming back the other way. But in a reversible reaction, where you get with a weak electrolyte, you do have sort of everybody kind of going in both directions. This case, it actually stays more to the left there and it stays together in solution. And obviously a non-electrolyte, as we talked about, is something that will still dissolve, if, for example, in water. But again, because there is no ions that are produced, it will not conduct electricity. So still will dissolve, no ions, no electricity being conductive. Any questions on any of that there? Now, as I mentioned, water and a lot of things are a very good solvent to use. And that's really because water is polar. So what happens when you take something like water, basically the oxygen side is more negative, the hydrogen side of water is more positive, as we talked about with bonding. And that works polar. So things that are ionic and things that are polar, this is a pretty good solvent to use. And what happens is, for example, when we do take something like sodium chloride, a solid, and we dump it into water, basically it'll break apart into its ions. So we have positive ions, we have negative ions, and basically each of these ions pretty much gets surrounded by a bunch of waters. And the positive ion would be surrounded by actually the negative side of water, which is the oxygen. Opposites attract, so the negative side attracted to the positive side. And the negative ion, say like the chloride ion, would be surrounded by the hydrogen part of water, which is the more positive part. So it gets surrounded by the hydrogen side there, basically, of water. And this basically does a couple of things. This basically allows for something like sodium chloride to dissolve. And to us visually, we can't really see it anymore, right? Because it's surrounded by a bunch of waters. It also keeps those two ions, which are really attracted to each other, apart and sort of buffered from each other, and not allowed to kind of come back together. We know it's still there. We know it's a physical change, right? When you take something like sodium chloride and dissolve it in water, because we could simply heat this up, right? And we evaporate off all the water. The two ions then can now come back together, and we get the solid back, which I think we did a couple of experiments early on where we evaporated off the water. We're left with like a solid in our evaporating dish and stuff like that. So water works really well with ionic things because they could do that basic attraction, positive, negative attraction, electrostatic attraction to one another. It works really well with polar molecules as well, because if a molecule is polar, it has a positive side and a negative side if you have a polar molecule. And that means that when you got your water there, it can do the sort of attraction between the negative side of water and, for example, the positive side of that polar molecule. So those things work really well together. What doesn't work well with water is something that is nonpolar, because if you remember, nonpolar basically means that we have equal sharing of electrons, right? And overall, the thing is kind of like neutral, if you will. There is no positive side, there's no negative side, because overall there is that equal sharing of electrons. So when water and something that's nonpolar get together, they're basically trying to operate on different ways. Water wants to do some type of positive negative attraction, and really the nonpolar guy could only do like a temporary kind of positive negative attraction. So over the long period of time, they have no way to keep that interaction going. So they oftentimes will separate out from each other, kind of like oil and water, right? Eventually they'll kind of float to the surface, right? And they kind of separate out from each other, and they have no real long way to maintain that. Or even like, right, when you mix it up, right, it's mixed for a bit, but eventually it all kind of separates out. It has no long way to sort of maintain that interaction. So this process is, again, what's sometimes referred to as hydration. It really is, when we write something like this, like a sodium ion that's aqueous, or a chloride ion that's aqueous, that aqueous is basically all these waters that are basically surrounding the ions. It makes for a much less complicated formula, but that's sort of what's happening there when we kind of have that. And again, keeps those ions from coming back together and remaking that solid. So as I mentioned before, acid and bases are also electrolytes. And again, that kind of list I wrote on the previous slide of a lot of the strong acids are good to know, because that basically means that they will, again, 100% break apart. So once again, the hydrochloric acid, 100% of what you have in solution is over here. And that's also, by the way, why they are considered strong acids. The basic definition of an acid is basically the ability to produce hydrogen ions, which means that this is a strong electrolyte and it completely breaks apart. As soon as that goes into solution, it creates a lot of H+ really quickly, which is why it's considered a strong acid. On the other hand, we do have some weak acids that are also weak electrolytes. This is acetic acid, also sometimes written C2H4O2, same thing. Again, we see our arrows heading in both directions. So things like acetic acid is a weak acid, hydrofluoric acid, nitrous acid, carbonic acid, and so forth. So these are all some weak acids that are also weak electrolytes as well. There's also weak bases that are also weak electrolytes. Something like ammonia is the most common sort of weak base that you come across a lot. NH3 is a weak base as well. So that leads us into talking about ways to classify reactions. And really all sort of reactions, for the most part, can be classified in kind of one or two ways. They kind of fall under two big umbrellas of reactions. The first big umbrella of reaction are double displacement reactions. And in a double displacement reaction, it has a general form of AB plus CD. And what these guys are ionic compounds. So a positive and negative guy, a positive, negative. Whenever you have a positive and negative guy together, what always happens is basically the two positive guys will switch partners. So on the other side, you make two new ionic compounds. And basically double displacement reactions takes care of two of the three reasons it takes place. So if you remember, there's basically three reasons or three driving forces for why a reaction takes place. It is the formation of a solid, or a precipitate is sometimes referred to. It is the formation of water. And it is an electron being transferred, basically. These are the three real reasons that you pretty much could boil down most reactions to as to pretty much what is happening. And double displacement reactions basically takes care of one and two, the formation of a precipitate. Our water happens a lot in double displacement reactions. So for example, in a precipitation reaction, one of these guys makes a solid. And obviously in a reaction where we form water, one of these guys is water is formed. So double displacement reactions really takes care of those two reasons. The other big classification of reactions that we'll talk about are what are referred to as redox reactions. And they basically take care of the electron being transferred, or electron transfer. So between sort of those two classifications, there are really more specific classifications that you could classify a reaction by. So what I mean by that is you could look at one reaction, and depending on sort of what you're looking at, for example, there could be, for example, three different ways that you could classify the exact same reaction, sort of depending on sort of what you're looking at. So you can definitely, as we will see, when we look at reactions, classify them in different ways. So the first one we're going to talk about is a precipitation reaction, which does fall under the double displacement sort of banner. So a precipitation reaction is a double displacement reaction. And what happens is when we sort of recombine those ions on the product side, that combination results in a solid beam. Solid beam formed is what's referred to as a precipitate. And a precipitate is sometimes abbreviated as a PPT. So sometimes you'll see PPT written, and that stands for a precipitate. So precipitation reactions usually involve ionic compounds. And once again, they are, although they are a more specific way of classifying a reaction, they are still ultimately are double displacement reactions, where basically the A ends up with the D, the C ends up with the B, and again, making those new ionic compounds where one of these guys will make a solid. So for example, if you take a little silver nitrate and you react it with some sodium chloride, this is a positive negative guy, that's a positive negative guy. So what's going to happen in this reaction is the silver will change partners and hook up with the chloride. The sodium will change partners and hook up with the nitrate. The result of this reaction is we will make sodium nitrate, and we will make some silver chloride here, which actually is a solid. And again, we made two new ionic compounds. And this would be a white precipitate that would be made. We sort of made that a while back when we did that experiment with the filter paper and you took it to the UV light, right? You sort of made some of that, I believe, if I'm not mistaken, in that case. So how do you know if you make a solid? We're going to talk about how you can figure that out in just a bit here. But again, it is a double exchange that occurs, and we do make a solid as a result of it. Here's another example of a precipitation reaction. And again, if we look at this, and I think on your notes it's fixed, but if not, there should be a 2 there, I think. So this again is a positive and negative guy. This is a positive negative guy. So what happens is our lead switches partners and our sodium also switches partners here, making us lead 2 iodide, which we will make in a lab coming up. Nice yellow solid. And we get our sodium nitrate, once again, a positive negative. So again, a double displacement reaction here, and also a precipitation reaction because we did make a solid in this particular case. Now, the equation that we see up there on top was referred to as the balanced molecular equation. It is pretty much everybody written in their normal formulas together. But really in solution, for example, we could write another equation that really sort of describes what is happening in this case. And that's because we do have a bunch of strong electrolytes here. So for example, in solution, this guy here, which is a strong electrolyte, will actually break apart. And what you would have is you would have some lead 2 ions floating around. You would also have a couple of the nitrate ions floating around. The 2 here comes out in front when you do that. The sodium iodide would also be a strong electrolyte. So you would have 2 of the sodium ions floating around. And you would have 2 of the iodide ions floating around. And that comes from distributing this 2 to each of these guys. Now, on the other side, we do have a solid that's formed. And really, the only way a solid could form is they have to stay together in solution, right? Because otherwise, you have a solution, you have the solid that's in there. So they will stay together. So when we're writing this equation here, we would keep something that's a solid together. We would also keep something that's a liquid together, and we would keep something that is a weak electrolyte together. So we will keep the solid here together. But this guy here will also be a strong electrolyte, which means in solution, you have a couple of sodium ions floating around and a couple of nitrate ions floating around. And once again, that is the 2 being distributed to both of those guys behind it. Now, this equation that I just wrote basically describes what is going on in this particular reaction. This type of equation is what is referred to as the total ionic equation, or sometimes it's just referred to as the complete ionic equation. It is a total ionic equation. Ions mean that they should have charges. So when you write this type of equation, you should always make sure you include the charges with anything that is an ion. You keep together, like I said, anything that is a solid, you keep together. Anything that's a liquid, you would keep together. If you happen to have a gas, you would also keep it together in most cases. And anything that is a weak electrolyte, you would actually keep together. So those sort of 4 things: solid, liquid, gas stays together, and anything that is a weak electrolyte should stay together as well. The importance of this equation is if we look really on both sides of the arrow, there should be some ions that are exactly the same. And if we look at that here, well, there definitely is the couple of sodiums here, which match the couple of sodiums on the other side. There's also a couple of, not that guy there, wrong choice. Get that without again. There we go. Let's go highlight the right one here. There's also a couple of nitrates over here, which match the nitrates that are over here. So these guys, which are ions on both sides, they are what are referred to as spectator ions. So those are spectator ions. And if you are a spectator, you're pretty much just watching the same idea here. The spectator ions are pretty much not contributing to the actual product that's being made in this reaction. They're really just there to balance out charges. They're kind of floating around, but they're really not going to make any of the product. And what we typically do is with the spectator ions, we cancel them out, because you can think of the arrow like an equal sign, so you can subtract them to the other side, and they should cancel out completely here. And what that third type of equation, which is really important, it leaves us what is left over, which in this case would be our lead with a +2 charge. Going to find 2 of the iodide ions that are floating around, and those guys are going to come together to make this solid. And this equation here basically tells you exactly what is happening when you mix those 2 things together. It is the lead 2 ion from the lead 2 nitrate. They're going to come together and make a precipitate, obviously. This equation here is what is referred to as the net ionic equation. And it is pretty much the bare bones equation that tells you exactly what is happening in that reaction. So when we do this reaction here, we get rid of all of this stuff that's just floating around. It is really just those 2 ions coming together to make the solid. So these are 3 really important types of equations. Molecular equation, we write everything with their formulas together like normal, balance it. Total ionic equation, we break apart anything that is a strong electrolyte into ions. Anything that's a weak electrolyte, a solid, a liquid, we keep together. We find our spectator ions in the total ionic equation. And what that leaves us is, after we cancel those out, the net ionic equation, which again is truly what is happening in this reaction. Any questions on that there? So that is, again, pretty much what this shows here. So I jumped a little ahead there, a couple of slides. So again, our total ionic equation, and once again, also important, make sure you do include the ions and the charges there that go with the ions, really. That's a very common thing that people miss. So once again, here, canceling out our spectator ions leaves us with our net ionic equation, which is really important. So if we look at another example like the one I wrote earlier, where we had our silver nitrate plus our sodium chloride, making our sodium nitrate and our silver chloride. So why don't you take a second, write the total ionic equation and write the net ionic equation and ID the spectator ions here. Second or two, see what you come up with. Okay, let's take a look. So again, pretty much anything that's got the aqueous symbol, you most likely will completely break apart. It's most likely a strong electrolyte, as long, again, as it doesn't fall as a weak electrolyte. So, as long as it's not one of those weak electrolytes, you can probably safely assume that it's going to completely break apart in solution, which means in our total ionic equation here, we're going to break apart our silver nitrate into a silver ion plus a nitrate ion. Our sodium chloride will also break apart, so we will break that apart into a sodium ion and a chloride ion. Once again here, looking on the product side, we got this aqueous guy, which is going to be a strong electrolyte. It will break apart into its ions here, which is a sodium ion and a nitrate ion. And our solid here will stay together. Otherwise, once again, it will not be a solid if it didn't. So again, we would keep it together. So this would represent the balanced total ionic equation. Again, the importance here, we have ions, so they have charges, very often forgotten by people when they write it. So you got to make sure you include those charges. At this point, we could use this equation to identify our spectator ions. And what we're looking for are ions on opposite sides of the arrow that are pretty much exactly the same. So if we look here, we definitely have a nitrate, right, which is exactly the same as the nitrate we see here. We also have a sodium on the left-hand side, which matches the sodium on the right-hand side. So those two guys definitely would be our spectator ions in this case. And in this case, it would be the sodium ion and the nitrate ion that are our spectator ions. We do get rid of them. So we're just going to cancel those out. And they cancel out basically, again, like looking at the arrow as an equal sign, subtracting them to the other side. They basically cancel each other out. That leaves us our net ionic equation, which in this reaction, basically what is happening is the silver ion from the silver nitrate is going to find the chloride ion there from the sodium chloride, and you will make this white solid here that is a silver chloride in this case. Yeah. Yeah, so basically, if I'm going to draw a really bad time-lapse photo here, but so basically when you throw in your silver nitrate and your sodium chloride basically into here together, what happens is you will get all of those guys that will basically break apart. And just for simplicity, I'll just write one of each of these guys. And basically what's going to happen is when these two guys kind of see each other, they're going to be attracted to each other, and they're going to come together and actually form that silver chloride solid, basically. So I'll just draw it down here as like a solid. And what happens is the remaining ions, if we kind of take those out of solution at this point, the remaining nitrate and sodium ions, they're still just floating around, but they're really not doing anything. So it's kind of the liquid part, if you will, kind of floating around, not making any of the solid. The real reaction that's happening here is actually the formation of that solid, which again is one of the three reasons why a reaction takes place, is the formation of the solid. So in this one, it's really those silver and chloride guys coming together. That's why we kind of cancel them out to get to the net ionic equation, because really the net ionic equation tells us exactly what is really taking place when we mix those two guys together. Other questions? Yeah. All right, so how do we know, if we put two things together, will we get a solid formed or not? We actually use what is referred to as solubility rules to help us decide that. We saw an example of solubility rules in an earlier experiment where on that post-lab question, they had like a little table where you move your fingers together to a box and it said I or S or something like that. That's really a solubility table. And when we talk about solubility, solubility basically is if one thing dissolves in another, it is soluble. If something doesn't mix together and they really don't dissolve, it is insoluble. So if something is basically determined to be soluble, in terms of sort of how we would label the formula, they get the aqueous symbol. So they get that AQ symbol next to them. If something is determined to be insoluble, what that basically means is they're really not going to mix. So if we're talking about like a solid in a solution or a liquid, we will still have the solid there. And that basically were the guys that will get this solid symbol next to it. So if something is insoluble, it is the solid. If something is deemed to be soluble, it's going to be aqueous. And what that really means is they're just going to be still floating around basically in the solution, like the sodium nitrate example a second ago. They're not going to make anything. So when we talk about it, soluble and insoluble is mainly the things that we see. Occasionally, you sometimes come across things which are labeled as slightly soluble, and it sometimes has like an SS sort of symbol next to it rather than like an I or an S. And slightly soluble in most cases kind of lean towards being insoluble. Slightly soluble means that, just like the name implies, some of it will dissolve and some of it won't. So there is a degree of solubility for everything, even things that are technically insoluble based on rules have some degree of solubility, as you will learn if you take 1B, things that we typically think about in terms of solubility rules, which is being insoluble. Under certain circumstances, they could still be soluble when they come together. Has some things to do with pH and concentration and stuff like that. Yes, sir. There you go. So they're all kind of similar type of terminology, but in the most cases, we will pretty much see either soluble or insoluble as mainly the two that you deal with. And again, slightly soluble does come up. So these are solubility rules that help us sort of determine when we put sort of two ions together, like we're doing here in this type of reaction, would we expect a solid to form or no solid to form? And the first rules that we're looking at are things that are typically soluble in water. And that means that these are typically things that will get the aqueous symbol. So the first rule is a pretty good one. It is pretty much anybody from group 1 on the periodic table is always going to be soluble. There are no exceptions. So when you see a formula that has sodium in it, that's pretty much as far as you need to look. You will know that it's going to be soluble. You can put the aqueous symbol next to it. You don't really have to look too much further. Anything that has ammonium, so not ammonia, but NH4 plus in it, is also going to be soluble in all cases. Once again, there are no exceptions here, which means if you see a formula that has NH4 in it, put aqueous next to it, you will be fine. There are no exceptions. Those that contain nitrate, chlorate, or perchlorate are also going to be soluble in everything. So once again, if you see a formula that has any of those guys in it, you can know that it's going to be aqueous. Now, when we get to chlorides, bromides, and iodides, they are soluble, but there are some exceptions. So there are 3 important exceptions here. If you have a chloride, bromide, or iodine with anybody else, it's going to be soluble. But if it happens to be hooked up with one of these three guys here, that is silver, that is mercury 1, and that is lead 2, it is an exception, which means instead of being soluble, it's going to be opposite, it's going to be insoluble. So if we look here, any chloride, bromide, or iodine that has these three guys will end up getting the solid symbol. Anybody that has chloride, bromide, or iodine that is not containing silver, lead, or mercury will be soluble. So again, there are some exceptions here. Most sulfates are soluble, except for calcium and silver sulfate, which is slightly soluble, and barium, mercury 2, lead, which are insoluble. So once again, if you have sulfate, it should be soluble, except that it is hooked up with barium, mercury, or lead. So if you have these guys here, it is going to be the opposite and become insoluble, which means they would get the solid symbol. So this is why earlier when we did our silver and chloride together, the chloride here is soluble in everything except for silver, which means instead of being soluble, this is why this guy got the solid, as compared to sodium chloride, which chloride is soluble in everything except for silver, lead, or mercury, and that is not silver, lead, or mercury, so this is aqueous. And by the way, on this particular one, you could have just looked at the sodium and said sodium is soluble in everything, and that's as far as you need to go. So that is, again, the differences in those exceptions. So if something is an exception, it is the opposite of what it normally is. So normally, again, chloride, bromides, and iodides are soluble. If it's an exception, it would then become insoluble. Any question on those rules there? Now, there are some rules for things that are typically insoluble. So this list are guys that are typically going to get this solid symbol because they are insoluble. Hydroxides are typically insoluble, except when it's the alkali metals, which is group 1, basically. Barium, calcium hydroxides are slightly soluble. So once again here, hydroxides will be insoluble, except for basically group 1, which means if you have something that has hydroxide in it and somebody from group 1, it is going to get the aqueous symbol. So that would be sort of the exception there. Carbonates, phosphates, and sulfides are insoluble. And once again, we have the same exception, which is basically our group 1 and 2, our group 1 rule from the other slide. If you have any of those guys with group 1 are ammonium, they once again will go from being solid to being aqueous. Questions on that there? So for example, if we looked at the earlier equation here, are similar to the earlier equation. All right, so if we were to use our solubility rules here, when we look at the very first one, although we may not find lead, we do find nitrate, and nitrate is on the previous slide, right? And nitrate is soluble in everything, which means there's no exception, which means that this guy again should carry the aqueous symbol. When we look at the second guy here, we see potassium, which is group 1, which means group 1 from the previous slide is soluble in everything. That frankly is as far as you need to go. But if you weren't convinced, you could go to the I. iodides are soluble in everything except for silver, lead, and mercury. And in this case, there is no silver, lead, or mercury, which also means that it is soluble. So in this case, you can actually look at either one to help you decide, but really you don't need to look past the first guy there, which is potassium. And we know that this guy would be aqueous. Same thing coming to the other side here. As soon as I see the potassium, that really is as far as I need to look because it's group 1. It's going to be soluble in everything. And if I wanted to look past it, I could also look at the nitrate, which based on the rules on the previous slide is also soluble in everything. There's no exception. So they both tell us the same thing, that this guy is going to be aqueous. Once again, we may not be able to find lead, but we can find our iodide. And once again, our iodide is soluble in everything except for lead, mercury, and silver. And in this case, it is hooked up with lead, which means instead of normally being soluble, this is one of the exceptions. So it will be insoluble. And this guy will get the solid symbol here. Any questions on that there? So if I had this one here, let's do Na2SO4 plus BaSO, no, not that, BaCl. BaCl2 gives us a little NaCl plus some BaSO4. Do a little balancing there, I suppose. All right, use solubility rules there to determine the states of each of these guys here. As far as I need to go, this is going to be the aqueous symbol. It is going to be soluble because of that. Although we may not be able to see barium there, we can see chloride. And once again, chloride is going to be soluble in everything except for silver, lead, and mercury. And in this particular case, there is no silver, lead, and mercury in that formula. So that means it will still be soluble at this point and should be at the aqueous symbol. Coming to the other side, once again, as soon as I see the sodium, because there's no exceptions, that's as far as I need to go. And that is going to be aqueous. We once again could also look at the chloride if you want. Again, there's no silver, lead, or mercury there, so it will tell you it is soluble as well. Coming here, we will look probably at the sulfate. And once again, the sulfate is soluble in everything except barium, right? Being one of the exceptions here. And because that is an exception, this would make it then insoluble in this particular case, and it would get the solid. Any questions on that there? Now, if I take this equation here, and once again, we can write the total ionic equation from this. As the top equation, there would be the molecular equation. If we took this to our total ionic equation, this will now break apart into 2 sodium ions and a sulfate ion. The barium chloride would also break apart into a barium that has a +2 charge and 2 chloride ions. So when you're doing this total ionic equation, this 2 comes to the front of the chloride. Coming to the other side, our sodium chloride would break apart into 2 sodium ions and 2 chloride ions. And once again, the 2 here would be distributed to both of those ions when it breaks apart. And our barium sulfate would stay together here as a solid. This would be our total ionic equation, where we see here that the spectator ions are which ions? It is the sodium ion, that's the same on both sides, and it is the chloride ions, right, which are the same on both sides. So those would be our spectator ions in this case. Once again, to get to our net ionic equation of what's really happening when we mix those two things together, we cancel out our spectator ions, and we are left with our net ionic equation, which is really, it is the barium ion going and finding the sulfate ion, making our solid here our barium sulfate, which is our net ionic equation. Any questions on any of that there? Yeah. Truthfully, it doesn't, as long as they're on the correct side of the arrow. Most people, kind of like when we do ionic compounds and all those things, usually we go kind of like positive then negative. So that's usually why you kind of see it like that. But technically speaking, if you wrote the sulfate plus the barium ion going to their side, it's okay. Yeah. But usually people kind of go positive, negative, I guess. Yeah. Other questions? Questions on solubility rules, how to write molecular total ionic equations, net ionic equations, identify spectator ions. You need to be able to do this. Yes. Any questions? Yeah. All right. So talk a little bit about acid and bases, and acid and base reactions also do fall under double displacement reactions. So typically whenever we take a acid plus a base, we basically get two things. We get a salt plus water, and a salt is really just an ionic compound, and water here being formed again is one of those reasons why a reaction takes place. So unlike a precipitation reaction where you could visually see the solid has been made, when we do this type of reaction, you may not be able to actually see the water being made, but just the presence, obviously, of it being made is a reason why that reaction is taking place. A little bit about acids and bases. Acids have sour taste, and they cause the color change in litmus paper. So if you ever use litmus paper, if it basically turns to red, that is acidic or stays red. It will react with certain metals to produce hydrogen gas that we'll talk about a little bit later on in this chapter. For example, like a single replacement reaction here, which I think we might have done in some of these here, where you put your thumb over the test tube as it was making bubbles, right, and did your wood splint. That was the production basically of hydrogen gas being made as a result of this single replacement reaction here. Two there. Aqueous acid solutions conduct electricity. So again, as we talked about a little bit earlier today, if it is a strong acid, it will basically be a strong electrolyte and conduct electricity really well. If it's a weak acid, it will be a weak electrolyte. Bases, on the other hand, have a bitter taste. A lot of bases are soaps, drain cleaner and stuff like that. If you use litmus paper and it stays or turns blue, that basically means basic. And also strong bases are strong electrolytes, which will conduct electricity. And obviously weak bases will also slightly conduct electricity. Kind of your basic definition of an acid, as I mentioned before, is the ability to produce free H plus in solution. So free H plus floating around, also sometimes referred to as the hydronium ion. For all intents and purposes, these two things are kind of the same thing. Bases, basically the definition is the ability to produce hydroxide. So if something has the ability to produce OH minus in solution, it's considered a base. If something has the ability to produce H plus or H3O plus in solution, is considered an acid. So as we talked about before, our strong acids will 100% break apart. So once again, in solution, you have, for example, for our nitric acid, pretty much all you have in that solution is H pluses and nitrate ions floating around. You have none of the HNO3 sort of units still together. It will really 100% break apart. It is kind of like again, a strong electrolyte, a one-way street, where it is all pretty much just going out to the product side. And that is, again, basically what you have in solution. So I put that list up earlier. So once again, that's a list right there. We got hydrochloric acid, nitric acid, sulfuric acid. Once again, you could add it to your list there. Perchloric acid, hydrobromic acid, hydroiodic acid. These are all strong acids. It's really a good thing to kind of keep in mind as you go through chemistry. This sort of little list here of strong acids. I would almost say that if it is not one of these guys and it's an acid, it's almost a safe bet to think it's probably on the weak side. Yeah. So again, these are really your, I'll say, popular strong acids, or mostly strong acids that you come across, the most probably in chemistry. And again, if it's sort of outside of those guys, you could probably make a pretty safe guess that it's going to be on the weak side, like HF, for example, acetic acid, nitrous acid. So those guys, again, would be weak acids. All right, any questions on that there? I think we will lay it up there for now, I think.